Hi, I'm Mike Mulvaney from the University of Florida, Cropping Systems Specialist. I'm located in the far western panhandle of Florida, and today I'm going to be talking about how much peanut nitrogen is available to a subsequent wheat crop. So this is a phenomenon that we often see after peanut production, where we see this windrow effect. Here you can see a carinata in the top photo, carinata crop after after peanut, and you can see where these windrows were, and it's not some kind of planting effect because you can see the planter went 45 degrees across those windrows. This is clearly a windrow effect after peanut. This is not necessarily a nitrogen credit after peanut, even though oftentimes we do attribute this to a nitrogen credit, and it may be, but this is not a nitrogen credit due to peanut in and of itself, because in between these windrows there was also peanut. So peanut in itself is not responsible for this effect. Rather this is some kind of windrow effect. Now, in terms of peanut nitrogen credits, we do in the peanut growing region of the southeastern United States, generally we do recommend nitrogen credits after peanut. The range is, generally speaking, 22 to 34 kilograms of nitrogen per hectare. That's 20 to 40 pounds of nitrogen per acre. In some areas in Virginia and Oklahoma, they tend to be higher, but generally speaking, we're in the 20 to 40 pound credit range. Now, when we look at a review of the scientific literature, we can see that those nitrogen credits are not typically substantiated in the peer-reviewed literature. In Alabama, we've got a series of field and laboratory studies and litter bag studies generally showing no nitrogen credit after peanut. The field litter bag studies were able to demonstrate a smaller than recommended potential nitrogen credit. We found in North Carolina that we had higher nitrogen credits than those in Alabama, which makes sense. The further south you go, higher, more warmer temperatures, warmer climate, increased mineralization rates, and therefore faster decomposition and lower nitrogen credits available to subsequent crops, potentially. Now in Florida, recently published last year, we did field litter bag studies using different tillage regimes and different residue loads. Tillage regimes just means buried the litter bags or put them on the surface, and only at the very high residue load rates were we able to approximate those nitrogen recommendations, those nitrogen credit recommendations that are found in the extension literature. And in that case, we had to use about 6,000 pounds of residue per acre. Now, with the yields that we're getting these days, 6,000 pounds of residue per acre seems achievable. Not so long in the past, that would not have been feasible. There's some other studies that were conducted here internationally. There were some problems with some of these studies that I won't get into, but generally speaking, we see either zero nitrogen credits out of the scientific literature or smaller than or smaller nitrogen credits compared to those that are seen in the extension literature. The objective of our study was to evaluate peanut and cotton nitrogen credits to a subsequent wheat crop in a conservation tillage system. We did this over 4 site years in Citra, Florida, and in Jay, Florida. These are on sandy soils. Citra is a sandy soil, Jay is on a sandy loam. And our experimental design was a randomized complete block split plot design with 4 replications. The main plot factor was summer 1 prior to wheat. Summer 1, we had cotton, peanut, and fallow. Now the fallow is important so that we can make the determination whether or not the nitrogen credit is due to peanut residue mineralization, nitrogen mineralization, or possibly due to cotton nitrogen immobilization from those carbonaceous stalks. Maybe that cotton is sucking up nitrogen, and when we see a yield response due to peanut, perhaps it's a yield depression due to nitrogen immobilization after cotton residues, or maybe, in some systems it might be corn. Now, our split plot factor was nitrogen rates on wheat. So we had 4 different nitrogen rates ranging from 0 to 101 kilograms of nitrogen per hectare. And we did find soil inorganic nitrogen levels half the time, right? So in 4 site years at this surface, 0 to 15 centimeter depth, we did find that soil inorganic nitrogen levels were higher after peanut compared to either cotton or fallow. That makes a lot of sense. The residues are recently added. We're getting increased nitrogen stores in those upper surface, in the surface layers. We didn't detect those differences further down, which also makes sense because this was an early season effect. What did it do in terms of grain yield on wheat? Okay, so here I'm showing just peanut and cotton, right? We have 4 site years of data. I'm going to discount Citra 2016 and 17. Yields were very low. There were other yield limiting factors that went on in that site year. So let's look at the remaining 3 site years. In Citra 2017 and 18, it didn't matter what you used. You may have had a slight numerical increase on some of these treatments after peanut compared to cotton, but nothing statistically significant. Same thing with J in 2018 and 19. In some of these treatments, you may have had slight numerical increases in yield after peanut, but nothing statistically significant. The only time we see a significant increase in wheat yield production after peanut compared to cotton is at these low N rates, 0 and 34 kilograms of nitrogen per hectare. And there we do see statistically significant differences. We continue to see numerical differences at these higher rates, but it's not statistically significant, and the numerical differences are obviously decreased. Now that would make sense because as we swamp the system with higher rates of nitrogen, we would expect that nitrogen credit from any potential nitrogen credit from peanut to be decreased. So this would make sense. Now, what happens when we add the fallow treatment here? Does this fallow treatment look more like cotton yield or look more like peanut yield? And when we add fallow equation to these figures, we can see, generally speaking, it doesn't matter statistically. It doesn't make a difference if you're after peanut, cotton, or fallow in 2 of these 3 site years. The only time it did make a difference was at these low N rates in J 2017 and 18, where you can see that that wheat grain yields after peanut were similar to after fallow. In other words, wheat grain yields were lower after cotton compared to either after peanut or after fallow. And this would provide evidence for potential nitrogen immobilization after cotton rather than nitrogen mineralization after peanut. Now, to be clear, most of the time, it doesn't make a difference, right? But when we see a difference, it seems to be due to nitrogen immobilization after cotton. Now, like I was talking about before, here's what I'm trying to model here with these red lines is the yield difference between cotton and peanut as your nitrogen rates increase. And you can see those yield differences tend to decrease as we continue to add nitrogen into the system. So under a normal production system where maybe we're applying 90 kilograms of nitrogen per hectare to wheat, we can expect to see reduced nitrogen credits, potential nitrogen credits after a subsequent peanut crop. So what's going on, right? We had increased nitrogen in the surface soil layers early on in the season. We followed these plots with NDVI on a weekly basis, and you can see, generally speaking, after peanuts, these dark filled in circles, you can see higher NDVI values early season with some frequency. At least 2, maybe 3 of these site years, you can see increased greenness, increased NDVI after peanut compared to either after peanut or fallow. Now, that difference tends to disappear after about 80 or 90 days. Okay, sometimes, let's say in J17 and 18, it's not apparent at all. But when it's there, it does tend to disappear in around 80 or 90 days after wheat planting. So a lot of times we see an early season effect. We say, yes, I've got a nitrogen credit after peanut, but just keep in mind that those visual effects may be ephemeral. So in conclusion, we found that generally speaking, crop history was not significant, but when it was significant, the nitrogen credits were not different from the fallow control. So nitrogen credits after peanut were not different than a fallow control. In those cases, it appears that the non-legume, in this case cotton, immobilized nitrogen rather than what we might attribute normally as a nitrogen credit from peanut. Now, there's a lot of potential, these are questions that are difficult to really get a good handle on. Nitrogen 15 studies would be ideal, but they are difficult and expensive to put into a field setting. There's lots of potential issues here that could be going on with the research, but that's why we need a body of literature. And I'm not saying that this one study is conclusive in proving nitrogen immobilization by non-legumes or by cotton. But what we are trying to do is build a body of literature here to try to get at the question of nitrogen credits after, in this case, peanut, or in a larger sense, after legumes, and that would include, clover or soybean or something like that. And we're attacking those questions as well here in future research. So anyway, with that, I really appreciate your time. This is my first time doing this, so I hope the audio came out okay, and I appreciate your attention. Thank you very much.